Hey, welcome. Today, we're going to dig into a science that's, well, literally the foundation of our entire world, but it's one that most of us never even see. It's the reason our tallest skyscrapers stay standing and our longest bridges don't just sink into the ground. All right, let's get into the hidden world of geotechnical engineering. You ever think about this? I mean, look at the Leaning Tower of Pisa. It's famous, yeah? But it's famous because it's a structural failure. So what's the deal? What makes one building a timeless landmark and another one, well, a cautionary tale? The answer isn't just about the fancy architecture or the materials. Yup, it's the ground itself. We tend to think of the ground as just solid, right? A passive surface we build on top of. But that could not be further from the truth. It's actually a super complex and dynamic material that can literally make or break a project. And when we don't understand that material, when we get it wrong, the consequences can be, well, absolutely catastrophic. You see, ignoring the ground you build on is just a recipe for disaster. And that's exactly where our topic for today comes in. This is it. This is the field that asks all the important questions before a single shovel hits the dirt. Is this ground strong enough to hold a skyscraper? Is it going to shift or settle over time? What happens when water gets in there? Geotechnical engineering really is the science of predicting how the Earth is going to react to whatever we want to build on it, making sure everything stays put. So to really get this, we have to start with the most basic question of all. What actually is soil? Because to an engineer, it's so much more than just dirt. It's a proper engineering material with its own unique set of rules. You know what? Think of it like a kitchen sponge. You've got the solid part of the sponge. Those are like the little bits of rock and minerals. But then you have all those holes, right? The pores. And those pores can be filled with air, or they can be filled with water, or some combination of both. This simple three-part system, solids, water, and air, is what makes soil so incredibly complex and interesting to work with. So where do all these little solid particles come from? Well, they all start as solid rock. And there are two main ways rock breaks down. On one hand, you have physical weathering. This is kind of like taking a hammer to a big rock. You're just mechanically smashing it into smaller bits of the exact same stuff. That gives you things like sand and gravel. But then there's chemical weathering. This is more like rust on a piece of metal. It's a chemical reaction that actually changes the minerals in the rock, creating totally new, superfine particles. And that's how we get clay. And what's really cool is that a soil's whole life story is kind of written in its name. See, once these little particles are made, nature moves them around. And depending on how they were moved, by a river, a glacier, or maybe just the wind, they get a special name. So an engineer can hear a term like alluvial soil and immediately know, okay, this stuff was dropped here by a river. It tells them a huge amount about what to expect. All right, so since the ground can be so different from one place to the next, I mean, literally from one side of a construction site to the other, how in the world do engineers figure out what they're dealing with? Well, they have a whole toolkit of tests designed to basically read the soil's personality. And you know what the single biggest factor is, especially when we're talking about fine-grained soils like clay? It's water. Just the amount of water in the soil can completely flip its personality and change how it behaves. And this progression is absolutely key. Engineers have figured out there are 4 distinct states. If it's totally dry, clay is like a hard, brittle brick. Add a little bit of water, it starts to get workable. That's semi-solid. Add some more, and you hit this magical state called plastic. This is where it acts just like modeling clay or Play-Doh. But if you add too much water, it just turns into a liquid, like a thick milkshake. And those exact points where it transitions from one state to the next, they're called Atterberg limits, and they are crucial for classifying soil. Now, the real goal here is to put a number on this behavior. So engineers measure that Play-Doh range, the difference in water content between when it stops being moldable and starts flowing like a liquid. That number is called the plasticity index, and it tells an engineer so much. A really high index means it's a very clay-like soil that can handle a lot of water before it turns into a soupy mess. And believe me, not all clays are created equal. Some are way more plastic than others. Take a mineral called montmorillinite. This stuff is like a super sponge on a microscopic level. It's the key ingredient in what we call expansive soils, like the black cotton soils in India. When this stuff gets wet, it swells up like crazy. Then when it dries, it shrinks just as much, causing massive cracks in the ground and in any building that was unlucky enough to be built on top of it. So yeah, understanding plasticity, it's not just some academic exercise, it's absolutely critical. Okay, so let's connect all the dots here. How does knowing a soil's Plato range or how big its particles are actually translate into real-world engineering decisions? Well, let's look at another super important property, permeability. It's a fancy word for a simple idea. How easily does water flow through it? A soil with lots of gravel is like a coffee filter. Water just zips right through. But a really dense clay, that's more like a sheet of plastic wrap. Water isn't getting through that anytime soon. Okay, now look at this number. That is the approximate permeability of clay. It's 10 to the minus 6 centimeters per second. That's 0.000001. That is an absurdly, incredibly slow speed. And that tiny little number has enormous consequences. Because clay basically doesn't let water through, it's the perfect material to use for the core of an earthen dam. It creates a waterproof barrier. But for that exact same reason, if your house is surrounded by clay soil, it's a total nightmare for keeping your basement dry, because the water just sits there with nowhere to go. See? The right soil in the right place is genius. The wrong soil is a very expensive problem. And that really gets to the heart of it all. Geotechnical engineering is one of the true unsung heroes of our modern world. It's this massive, invisible science that makes everything else we build possible. Now, the whole field was really put on the map by one guy, Dr. Carl Terzaghi. He's known as the father of soil mechanics because he was the one who first created a system and a set of principles for understanding how soil actually behaves under the stress of a building or the pressure of water. So if you walk away with one thing from all this, let it be this. The ground under your feet is not just some passive stage for our buildings to sit on. No way. It is an active participant in everything we do. It swells, it shrinks, it shifts, it compresses, and it holds up immense weight. Understanding it is the first and honestly the most important step to building a world that's going to last. So the next time you're standing in a skyscraper or driving across a long bridge, just take a second. Think about that incredible hidden world of soil right beneath the surface, and the engineers who figured out how to speak its language, all to make sure that you stay safe. Makes you wonder, what invisible world is holding you up right now?